There will be a time at the end where we'll answer the questions. At that time also, you'll be able to pose an oral question if you would prefer to do it that way. And this is also being broadcast right now through Facebook Live. So if you're going to watch it that way, then you can also ask questions through Facebook. And just know also that this is being recorded for educational and documentational purposes. Okay, so just in case you weren't able to make it to the first webinar, just a reminder of who we are. We're the Pacific International Training Desk. We provide meteorology and communications-based instruction to people that work at the WSOs in Micronesia or in the various weather offices in the tropical South Pacific. So one of our past employees used to point out that the etymology of the word communication is sharing. So essentially what our purpose is to share. We're here we share the latest and greatest in meteorological science and in communication abilities, whether through satellites or the internet. So that's our demographic. And just speaking to them real quick, we now, thanks to the internet, we are able to surmount some of the COVID difficulties besides for with the webinars. We have our distance learning program that's about to, we're gonna run our first cohort at the beginning of October. And if you're interested in participating in that, then you should check out our website where you can find all the forms you need to apply for that. We also have more upcoming webinars. So far, I have planned for early October. We're trying to stay with a thematic progression. So it'll be climatology in the tropical Pacific for early October, particularly pertaining to El Nino impacts. And then in mid-October, I'm setting up one that'll be surf forecasting. So since our clientele who we teach to, they're all based in Pacific Islands, we focus on marine forecasting and even surf forecasting for them. So, we'll follow up, we'll send out flyers through emails, but if you want to check out Facebook or our website to see when those are, the exact dates are going to be, those will be posted pretty soon. Okay, so today's panel, when I put together the flyer about a week ago, I was really happy with the people I was able to assemble for today. So our first speaker is going to be Alison Nugent, who is an assistant professor in the Atmospheric Sciences Department at UH. She got her PhD from Yale, and her focus is on mountain meteorology and orographic precipitation, particularly with recent research into the effect of aerosols on the orographic precipitation. And then our second speaker will be Feng Hsiao, who recently graduated from UH. And his specialty is in warp mesoscale modeling of mesoscale effects around the island, Hawaiian Islands. He also maintains the daily model runs that we do for the Hawaiian Islands, Marianas Islands, and Samoa. So if you've been a Pacific Desk student, you've seen these before, and you know they're useful tools. And he also he's a co-investigator with PAC-IUS, because PAC-IUS uses those model runs for their high-resolution nearshore wave models. And then our final speaker will be Liye Li. She also graduated from the University of Hawai'i in 2015 with a master's degree in meteorology. And then she went back to China, and she worked at the Foshan Tornado Research Center. So if there's time for questions at the end, my question will be about that. And she did tornado surveys. She's currently at the University of Chinese Academy of Sciences in their PhD program for severe mesoscale weather. And before I pass it on to our first panelist, speaking directly to our past Pacific Desk students. So some of the topics today are a little sophisticated, but they're all based on concepts that you've seen before. So in the past, we've talked about mesoscale weather as island scale. So this is weather which is affected by the terrain directly usually. And these are on spatial scales of typically under 500 kilometers down to 10 kilometers, and in temporal scales of a few hours. So in our first exercise in level 1, we have flow that goes over a mountain. And the convection that's produced there is by orographic lift. And then the flow, as it continues over the mountain, it descends in the Liye, and the air warms as it's compressed on the other side. So orographic lift, and then we also discuss sea breeze, land breeze effects. The land surface has a lower heat capacity, so it warms up faster than the neighboring sea. This causes lower pressure over the land surface. You get airflow blowing in from all sides of the island, and then in the afternoon you can get convergence and convection from that. So our speakers will discuss these concepts, but within consideration of all the complexities inherent in real terrain and a variety of land surfaces, as well as the complications arising from different synoptic situations. Okay, so with that, I would like to pass it on to our first panelist, who will be Alison Nugent.
Thanks, David. If you can stop sharing your screen, I'll share mine. Okay. Just moving the Zoom things out of the way. Okay, thanks for having me today. My name is Alison Nugent. I'm an assistant professor in the Atmospheric Sciences Department at Manoa. And today I want to talk to you about flood and fire enhanced by terrain effects in a hurricane environment. I think this topic was particularly requested because it's really relevant right now with all of the fires that are going on the west coast of the United States. So some of the things will be relevant to that as well. So before I go forward, I want to acknowledge some collaborators on this work. On the left is Gavin Shigesato. He's in the National Weather Service Honolulu Forecast Office, and he's a former master's student with my group. And some of the work I'll show is part of his master's thesis. And then on the right are a number of collaborators on the BAMS paper, Fire and Rain, the Legacy of Hurricane Lane in Hawaii, including Clay, Ryan, Tom, Henry, and Maddie. And a little bit more about me and my research. As David said, I do mountain meteorology work, and I focus on cloud microphysics. So the word cloud that you see in front of you is kind of an overview of my work, with the size of the word showing how frequently it appears in abstracts for research conferences. You can see I do a lot of work on clouds, precipitation, convection, mountains, tropical weather, islands, and so on. And this was already introduced, but I think it never hurts to have a reminder. When you have your spatial scales on the y-axis and time scales on the x-axis, you can go from microscale processes up to global scale processes, and seconds to minutes up to days or more. So in this mesoscale processes discussion, we're talking about things like hurricanes and tropical storms, which are kind of on the border between mesoscale and synoptic scale, and things like thunderstorms or mountain meteorology, mountain valley breezes, and so on, which are purely in the mesoscale. And in particular, I'm going to talk about how the environment of Hurricane Lane, which set the background environments that affected the islands, combined with the topography of Oahu, influenced local precipitation and wind, which led to flooding and fires during this specific event. A little bit more about mountain meteorology. It's the study of how mountains modify weather and climate. So for example, their influence on clouds, like in this image of a lenticular cloud, which we only very rarely see here in the tropics. And mountain meteorology could also be influenced on precipitation, winds, vegetation, habitability, and so on. And so on the right-hand side, these images are from Tom Jambuluka's Rainfall Atlas. You can see that in this mean annual rainfall map of the Hawaiian Islands, we have our trade winds coming from the northeast, and it leads to this precipitation maxima along the windward slopes of all of the islands. And this is because the trade winds are being forced up by the mountain slopes, causes the air to expand, cool, and condense, and puts rainfall right there on those windward slopes. So this is what we see in a basic scenario. Now let's put it into this context of Hurricane Lane and see how these island effects affect precipitation and wind and rain and fire and things like that. So today I'll be talking to you about Hurricane Lane, which occurred from August 18th to 28th in 2018. You can see on the left, the track of Hurricane Lane is this white dashed line here, with the cyclone symbol showing the strength of the storm from tropical storm category up to a maximum of category 5 on August 22nd. And then it approached the islands and then took a left turn. On the right, I have each of the main 4 islands with the terrain peak labeled just for reference. And to get down into it a little bit more, here's the graphic cone of uncertainty through time for Hurricane Lane. Again, it peaked on August 22nd with 160 mile/hour winds, 926 hectopascal central pressure, just around 500 kilometers southeast of Hawaii. And luckily, as it approached the state, vertical wind shear played a strong role in both weakening and curving the track away from the state. So the legacy, what Hurricane Lane left behind was fire and rain. So this image kind of puts all of everything into one summary slide. These dots on each of the islands show an individual rain gauge and the rain gauge rainfall total over 4 days from August 22nd through 25th. The primary impact of rainfall was on the east side of the Big Island. Those were the windward slopes where the air was being pushed up against. And in particular, you can see the 4-day rainfall totals saw up to 1.4 meters of rainfall, all in this area right around Hilo. Other islands got rainfall, but not nearly as much. What doesn't stick out as much from this image are these little red areas on the lee sides of Maui and Oahu. So I'll kind of blow those up a little bit bigger. What those areas are showing are fires on the lee slopes of both of those islands. So in addition to the rainfall, there were simultaneous fires in leeward areas on Maui and Oahu that, at least at the time of the storm, were not necessarily attributed to the storm itself, but after the fact, we can see that they were. Here's a picture of the Maui fires and the burn scar that it left behind over by Lahaina in West Maui. And here's some images of Big Island flooding during the event. So research questions and a possible contradiction. How can a hurricane be responsible for both fires and extreme rainfall at the same time? So in past research, we can see that hurricanes and fires have been connected, but usually after the fact. The hurricane comes by, knocks down a bunch of trees, and then those trees are the debris that later burns. But in this case, we had fires that occurred as the storm was approaching, not after the fact. And then second, we know, as just from that introductory slide even, that orographic uplift of moist air is common on windward slopes of islands. But what can we learn from the observations about how this event enhanced the orographic precipitation from the storm environment? So the data sources that I'll be using are a number of rainfall sources, 156 rain gauge stations across all the islands, a 25-year daily rainfall map from Longman et al., and 2 operational NextRad radars shown here. For atmospheric conditions, we dug up some weather stations. We have the National Weather Service weather station from Honolulu, also one from the Kaleloa Airport, and one from Lahaina, because those were the closest locations to the fires. We're also using radiosonde balloon soundings from Hilo and looking at fire extent and vegetation mapping from satellite imagery and land cover products. And here I'm going to kind of jump to the end and put it all together, and then I'll step back through it. So what we found was that during Hurricane Lane, the lee sides of Oahu and Maui were ideal. They had ideal weather conditions for fires. The Honolulu National Weather Service fire weather red flag warning criteria is given in the red box on the left. when the relative humidity is less than 40%, when wind speeds are greater than 20 miles per hour, and those conditions are sustained over a number of hours, and when the KBDI index is greater than 600, you have the conditions for a red flag warning. The KBDI indicates the quantity of rain necessary to saturate the soil. So therefore, a value like 600 KBDI means that you need 600 millimeters to saturate the soil. So it indicates drought conditions. What we found was that during the approach of Hurricane Lane, all red flag criteria were met just prior to fire ignition. And the reason is kind of summarized on the right-hand side. You have Hurricane Lane shown here. The moist region is in blue, the dry region is in white. And you can see that Big Island is in this moist region, but Maui and Oahu are still influenced by the storm. They're still getting that storm wind, but they're on this dry side gradient. So what we believe happened was that dry northerly air was pushed up over the mountains for Maui and Oahu, and it led to lee side acceleration, adiabatic compression, which led to warming and drying of the air in the lee side. But the hurricane part of this is that during hurricane storms, where the eye is, you have intense upward motion. But then just outside the periphery, the air needs to go somewhere. So in the eye wall, it shoots up and then it slowly sinks outside of that. So you have this slow subsidence all around here in this dry region, which did two things. One, it enhances this adiabatic compression, warming and drying, but it also enhances this lee side acceleration. This purple dashed line is in part there. And in fact, the reason why you have this capping layer where the air isn't able to rise over the mountains, instead it gets squished into this smaller region and therefore has to accelerate. That's in part because of the subsidence from the storm. And so while Big Island was on this moist side, the dry subsidence region caused the warm, dry conditions that affected or led to fire conditions. So fires are typically not predictable. They're just induced by human activity, and it's more the weather conditions that determine whether or not they can spread. I'm just showing this image so that if you want to come back, you can have another look at it. I do want to move on so that we can talk about more things, but this shows KBDI through time from early July through September, and you can see it just increased prior to the fire ignitions, which are these red vertical lines. You can see that the winds and the winds were high and the relative humidity was low just prior to fire ignition. Okay, so then the question is this hurricane and fire connection thing, is this a one-time thing or has this happened before? I'll say I don't know, more research is needed, but I've looked into it a bit. And one thing that sticks out to me is that the hurricane season and the summer dry season coincide in the Pacific. That's not true in the Atlantic. Hurricane season is not the same time as dry season. And so, at least for the Hawaiian Islands, this is unique. Hurricane season and the dry season coincide. So KBDI is often high as hurricanes pass. Also, if we look at this warm, dry region surrounding storms, which we've coined the term Hurricane Lei, these are visible in other storms. For example, Hurricane Hector, which occurred before Lane in 2018, and Olivia, which occurred after, both have these Hurricane Lei features in water vapor satellite imagery. So we can't say whether or not they actually affected fires, but it's possible that they could have, and it's something that more research needs to be done into. Okay, so now let's look at the rainfall from Hurricane Lane. On the left is the cumulative total over August 22nd through 25th. And you can see most of it was in this Hilo region as well as the southeast side of Big Island. And what was shocking about this is that Big Island received, in some locations, 1/4 of the annual rainfall. 1/4 of the annual rainfall in 4 days. Like, that's really impactful. And not only that, the record-setting rainfall occurred 4 days in a row. On the right, you can see the storm is just outside of the view of the radars, at least at this scan angle. But what I want you to look at is the southeast side of Big Island. Over this entire radar loop, rain occurs on other islands sporadically, but it's continuously occurring on those windward slopes and kind of the southeast side of Big Island. This was continuous over the entire time period. So I'm bringing this up because when you think about extreme rainfall, it can result from two different things. You could have high rainfall intensity, so high up on this y-axis, but a short rainfall duration. So you could be up here, or you could have low rainfall intensity over a long duration. So over on the right on this extreme rainfall kind of phase diagram, or you could have both. So let's look and see what it was about Hurricane Lane that resulted in this extreme rainfall. This is an image from Gavin Shigesato's thesis. He looked at the maximum radar rain rate on the first day, August 22nd, over an 8-hour period. And what this is showing is just the instantaneous maximum radar rain rate reflectivity. And he found that there were rain rates as high as 10 inches per hour found on the windward slopes, just around Hilo. So this points to the high intensity, short duration side. Now let's look at it a different way. Let's look at the duration of time spent raining greater than some threshold. So we chose 1 inch per hour, and he looked at the number of hours spent raining, or the amount of time spent raining greater than 1 inch per hour. And he found that in some locations, again, just upwind of, or up the hill from Hilo, over 50% of the time, there were rain rates greater than 1 inch per hour over this 8-hour rain period. So this shows us that there was also a pretty good long rainfall duration as well. So what we found was that extreme rainfall from Hurricane Lane resulted from both a high rainfall intensity and a long rainfall duration. Okay. I wanted to connect this back, and I think David did a really nice job doing this at the beginning, but all of these things are things that you've learned before about mesoscale dynamics. So the rain and the red flag conditions can be related back to these basic dynamic ideas. On the bottom right is a simple image which would normally represent the dry adiabatic lapse rate. But in this case, I want to point out that on the windward side, lifting, so this blue arrow here, and this side of the mountain where the air is being pushed up, lifting causes expansion, cooling, cloud formation, and rainfall. And I just showed you that these conditions were sustained over a 4-day period, leading to flooding and landslides during Hurricane Lane. Now, if we look on the right-hand side, we could see that on the lee side, lowering of air causes compression, warming, and drying. And this was accelerated in part because up above the mountains, we had really strong winds from the hurricane environment, which mixed down, enhancing the downslope winds and then enhancing the warming and drying. And then that subsidence from the storm compressed the air even further, causing this acceleration effect to be even stronger. Okay, so up the top, I've already provided good evidence for this, that Hurricane Lane was responsible for both fires and extreme rainfall simultaneously due to the storm boundary between that moist and dry side and the interaction with terrain. But there's a few other points that I think are really interesting that I'd like to point out. One is that we noticed from this event that there was a complication to emergency response. So simultaneous occurrence of high winds, fires, flooding, and landslides occurring on different islands or sometimes different locations within the same island, it strained the capacity of emergency responders. So they weren't able to respond to other emergency issues like clearing the roads or that kind of thing. The high winds prevented the use of aerial firefighting. So that means that it put more firefighters in danger, it took more of them, and it took longer to put out the fire because they weren't able to use their helicopters. Landslides blocked access to communities. So on the northeast side of Big Island, there was 14 landslides along that stretch of road. And in some places, that road is the only road in order to reach these communities. On Maui, one of the fires caused the closure of a hurricane shelter within 12 hours of expected onset of tropical storm force winds. So imagine you're stressed out, you're going to go to a hurricane shelter to protect your family, and then you have to leave the shelter because there's a fire evacuation. So a lot of these things added up. In addition, we looked at how these types of events can lead to, future food supply issues, especially if there's damage to shipping ports or airports. And then the last one at the bottom, I think, is one of the most interesting things that this project taught me, was that the change of managed land, so cattle and farming, to unmanaged land, and residential development enhances the risk of fire. So what we saw was that over time, there used to be a lot of farming, there used to be a lot of cattle ranching, but then the price of the land got so high that it made sense to sell it residentially. And so you have these residential communities with multi-million-dollar homes right next to unmanaged grassland. And that is a recipe for disaster. And that's exactly what happened in West Maui and happens in many places on Oahu as well. So that's all I have about that. If you'd like to look into more detail into this particular study, you can see this paper at the bottom, Nugent et al., Fire and Rain, the Legacy of Hurricane Lane in Hawaii. And if you want to contact me, feel free to email me, follow me on my Instagram, or check out my website. That's all I have. Thanks.
All right. Thank you, Allison. So I guess, yeah, we'll wait till the end for questions. So our next presenter will be Feng Hsiao.
Aloha, can you hear me? Can you hear me?
Yes, we can hear you.
Okay,
Yep.
okay. Oh, thanks, David. So I need to share screen. So thanks, David. I'm glad to be here. So I would like to share some information of the local heavy rainfall event under weak wind condition, especially over the central Oahu. That's a quite dry area. This event special occurred under the seasonal transition. This work, I cooperate with my PhD advisor, Yinan Chen and David. This figure shows mean annual rainfall from Hawaii rainfall atlas. Alison also showed this figure. So I think this figure tells a lot of story. So first, it shows very high spatial variability over the Hawaiian Islands. For islands with mountaintop below the tradewind inversions, like Oahu, Kauai, and Molokai. The annual rainfall maxima occurred over the mountaintop because the mountaintop below the tradewind inversion. So for the other islands like East Maui or Big Island, the rainfall maxima occurred over the windward slope. So the annual, the terrain and the local terrain and the tradewind inversion that affect the local winds and local rainfall distribution. So the island forcing is very important when we discuss the rainfall. Like for Oahu and Kauai, those those island mountaintop below the tradewind inversion, but the rainfall amount also very important, sensitive to the mountain height. So we can see here over the Oahu, central Oahu is relatively drier than the two mountain ranges. And the typical rainfall distribution is occurred over the mountain ranges. So over the seasonal transition, during the warm season, like May to October, we expect typical tradewind weather. Previous studies show the most rainfall pattern during the warm season are tradewind showers due to orographic lifting. So heavy rainfall events not expect occurred often during the summer or warm season. But we do find some heavy rainfall case over central Oahu, which is relatively dry than the two mountain ranges. There are these 13 cases, heavy rainfall event. Most of them occur in June and October, which we define as a seasonal transition. And these cases occurred, these cases are not studied before because we don't expect this kind of heavy rainfall case. So next, we do the composite analysis for all of these 13 cases. There shows 4 panels from the synoptic analysis of the 13 cases. This one shows the upper level. We see the omega blocking with upper level trough near the Hawaii Islands. At low level, we see the weak wind shear, or the course is Oahu. And the shading is high theta E. So we see the moisture is higher. And we can also see the total principal water. We see a moist tongue from tropic extending to the Hawaiian regions. And then from the profile, we see weak low-level winds, and the atmosphere is conditionally unstable. This is typical synoptic pattern for all these events. So next, we do a case study for more detail. With those precursors, we need to understand what is the physical process to initiate this convection. So we did a model simulation and observation analysis for this case. This case occurred on June 8th. From the storm event database, we see a heavy shower and thunderstorm struck central Oahu and caused flooding. And the heavy rainfall also resulted in the mudslide in the Kamehameha Highway that closed the highway for several hours. And again, we also check the synoptic condition. First, we see the upper level is a rex blocking with high low and shorewave trough around the Hawaii region. The red cross is Oahu Island. At low level, we see deep moist tongue across the Hawaii region, and low level wind is relatively weak than we expect trade wind days. So here is the observation from satellite image and radar echoes. Upper panel is the satellite image from visible and IR. So it shows the cloud is formed in the central Oahu and moves southeastward. The outbreak time is around the 14 local time. And radar echo gives us more detail with a high time resolution. So at the beginning, first echo is over the central Oahu around 12 and moves southward, and outbreak moves southwestward. And radar estimate rainfall also shows similar patterns. Then we do the model simulation to see the airflow pattern at the initial stage. The left panel shows the model simulation at a 10 local time. From left-hand side, we see clear onshore flow from all the coast. The shading is vertical motion at 900 millibar, and the contour shows the black contour shows the vertical motion due to orographic lifting at surface. So we can see on the windward side, we see the orographic lifting on the eastern and the western slope over the Colorado and Waianae Mountain, but the simulated vertical motion at 900 millibar is over the western and eastern slope of Colorado and Waianae Mountain and over the central Oahu region. So we see those vertical motions due to the onshore flow convergence from the north and south coast. Similar pattern we can see from the surface observation and radar echo. So we see at 11 local time onshore flow from the south, and at 12 we see the onshore flow from the north. So the first echo detect for this event is at around 12 local time. So at the 10 initial stage, from model simulation, we see the low-level convergence. So the time between the low-level convergence and the first echo detected from the radar, Molokai radar site is about 2 to 3 hours. Those time lag between those two imply the possible nowcasting for this event. And we can see the clear onshore flow maybe help forecast this kind of event. Next is the cross-section along southeast and northwest Oahu. So we see the onshore flow, the shading is the theta E. So the onshore flows on the south coast bring the warm and high moisture air to the central Oahu and converge with the onshore flow from north coast. And we have vertical motion in the central Oahu. The vertical motion reach about 1.5 kilometer. And we do the security log P plot at the central Oahu. We see the low LCL is around maybe 1.4 kilo. So once the air partial lift reach LCL, the condensation will occur and latent heat release will hit the air partial to ascending. Next, we see from the previous slide, we see low-level convergence due to onshore flow. And those two figures shows the mixed layer evolution. The left panel is theta, and the right panel is mixing ratio. So from time to time, 7 to 11 local time, we see the mixed layer growth from maybe 700 to 1.5. At 11 local time, so the mixed layer deepen also increase the temperature from maybe 296 to about 300. And the moisture also increase due to the onshore flow bring the moist air to the central Oahu. At 11, the height of mixed layer reach about 1.4 kilo, which is above the LCL. And this figure just compare the model simulation and observation. So after we did some modification to get a better boundary condition in the model, the simulated airflow is comparable to the observation. So we see the onshore flow and the radar echo over the central Oahu. So here I bring some short summaries from the review of the large-scale setting. A typical precursor for this type events are upper-level trough, and with a blocking pattern over the mid-Pacific in the mid-latitudes. And low level, we have a weak surface wind shear line, and the moist, deep moist layer, and the atmosphere is additionally unstable. And we need to weak low level wind to the island scale circulation to have onshore flow initiate the convection. But the onshore flow is related to the surface heating that deepens the mixed layer to LCL and establish the onshore flow brings the moist and warm air to the central Oahu. We have the schematic diagram simulate land surface heating over central Oahu that drive the sea breeze over that bring the moist air to the center, and we have updraft. So we also see the upslope over the eastern Wildland Mountain and the west slope of Coral Mountains. Those regions also shows the convergence, and at the early stage, there are echoes observed on the slopes. The initiation of the convective storm is caused by the convergence of sea breeze, and the build-up of the onshore flow and the first echo observed, the time lag between those two is about 2 to 3 hours. So now casting of this this event from observation is possible. So for more detail, we have refer this paper. And here I want to show a similar case in last year, in last September. So this is a visible image. So it shows a convective over its origin from the Oahu region. So this is total pre-spot. We see the high moisture over here, and from the upper level, we see a low, high, low omega plucking pattern. And from the surface, we see the shear line is around here and the weak wind condition. So we expect that kind of synaptic condition, we will have the maybe this kind of event occurs. So we also check the island scale from observation. It is from the local time, 10 a.m. So we see onshore flow from the south. It's clear. Also, we have similar pattern from our model simulation. This model is operational real-time forecast twice daily. And we can check the output every day on the link. So we also see the onshore flow from the north and south, and the model did have convection over Central Oahu. And that's all I have. Thank you.
All right, thank you, Feng. And our last speaker today will be Liye Li. Are you ready to go, Liye?
Hi, David, can you see my screen?
Yep, I can see you.
Okay, great. Hello, everyone. My name is Liye, and I would like to introduce the conditions favorable for the occurrence of trapped mountain waves downstream of Oahu. This is what I did during my master's, and my advisor is Professor Yilang Chen. I saw Alison show similar pictures of the lenticular clouds, and I believe many of you has observed this kind of clouds on the mountaintop or to the downstream of the mountain. And this is a very typical gravity waves with sufficient moisture to show the lenticular clouds in the atmosphere. And if there is a sufficient moisture, we can see the clouds. But what if there is no, and even though the sky is clear, but there may still exist some turbulence over and downstream of the mountain, which is a potential danger, especially for the aviation. And they may also have some downslope wind and hardly to be observed before. These are some events occurred before in Hawaii, like the strong winds, the flooding, and here is satellite pictures show the gravity waves to the eastern side of the mountain. And this is the turbulence impact on the flights. And this is from the model simulation. The vertical the W shows the oscillation downstream the island. So if we start from the theory, the lenticular clouds is actually showing an internal gravity wave, which means the atmosphere needs to be stably stratified, and there is a restoring force which is a buoyancy force, so that the L partial can go oscillate around the equilibrium level. And if we apply the Bose-Next approximation on the linearized internal gravity wave equations, we can get all those equations. And if we put all of those together and get one equation for the W, the vertical motion, we can have this formula. And the L square is the squirrel parameter, and it's composed by two parts. The first part is related to the buoyancy frequency and the steady wind speed. And the second part is the derivation of the wind shear over sea. And if we put the boundary conditions with this relationship, and we can solve a dispersion relationship, which is the L square equals M square plus K square. The K square is the K is a horizontal wave number, which is basically decided by the shape and height of the mountain, and didn't change quite a lot for a certain area. And the M is the vertical wave number, which decides whether the wave, how the wave can propagate in the vertical direction. And the value of the M is decided by L and K. So if the L square is over than the K square, which means the M can have a real solution, and the vertical propagation is allowed. And however, if the L square is smaller than the K square, the M square is less than 0. So the vertical propagation decays exponentially with height. And also the shear of the L square, the changing of the L square along with the height is quite well affect the wave. And if the L square decreases significantly with height, as shown by this figure, it will it's more favorable for the trapped Liye waves to occur. This is a simple two-level model. The L square down in the upper level is smaller than the lower level, and you can see the wave in the vertical direction is decaying, so it's propagating downstream of the island. And another important parameter is the flow number, which is the U over NH. The H is the mountain height, and it demonstrates how strong the airflow can go over the mountain or be blocked. If the flow number is over the 1, which means the airflow can't go over the mountain. And so this is related to how strong the wind is, and the wind and the static stability. Here is the terrain of the Oahu. You must be very familiar with. The mountain range is in the direction of the north-northwest and south-southeast. So during the winter time, if there is a cold front approaching, the southwesterly wind is perpendicular to the mountain. And actually, there are different types of mountain waves being observed over the Hawaii Islands. And I will show you one of the cases in my presentation, which occurred in the 27th January 2010. And all those are the settings and the parameterized scheme for my WRF simulation. Those three are the satellite pictures, and you can see the clouds that's shown by the lenticular, the wave shown by the lenticular clouds. At first, it's growing on the islands, then it's propagating and developing. And the wind is in the southwest direction, and in the developing stage, you can see the wave propagates a long distance, and it decays several hours. This is a vertical. Here is a vertical motion simulated by the model, and compared with the developing stage, it matches quite well. If we check the synoptic environment for these events, we can see a mid-latitude cyclone to the northwest of the island. Before the event is kept with the cold front is impinging the island, and the wind is pre-front southwesterly wind becomes stronger as the cold front getting closer and closer. So at this moment, it's a mature stage of the trapped mountain Liye wave. And after the cold front had passed by, the wave decays. So the synoptic condition for this case is the cold front to the northeast island of the mountain. And at the same time, the subtropical high is weakening and retreating eastward. And here is the soundings. The trade wind inversion is typically 1.5 kilometers in the wintertime over Oahu. And during this case, because the southwesterly wind is getting stronger and the inversion layer is elevated at the same time to 2.5 kilometers, which is above over the mountain. And the wind in low level changing from the light southerly wind to stronger southwesterly wind. And the wind shear at below 500 hectopascal has a significant increase in wind shear with height. Here, after the cold front had passed by, even though the inversion layer is getting higher, but the wind has changed its direction to light northwesterly wind. And so the Chapley wave ends. For the wind profile, another important condition for Chapley waves to occur instead of other mountain waves is the critical level. The critical level is the wind shift direction, and the wind speed is 0, as shown by the red circle. The wind change from for this case, the change from easterly to westerly, and at this point, the wind speed is 0. So for those two kind of cases, it is mountain wave and downslope windstorm occurred instead of Chapley waves. And the mountain wave is more concentrated over the mountaintop and compared with the Chapley wave, which is to the downstream of the island. And you can see here is the potential temperature and the relative humidity. It is more concentrated to the over the mountaintop and down slope to the mountain. So in a summary, the synoptic conditions for Chapley waves in the wintertime, the first is the presence of the inversion layer, which is very essential for the gravity wave to have a stable layer for vertical oscillation. And also it confines the moisture and heat flux from the ocean. And the second condition is the approach of the cold front. The prefrontal southwesterly wind is perpendicular to the mountain range, and the wind profile is increasing with height through the inversion layer, and there is no critical level. The inversion is lifted to allow the low-level vertical propagation. And here, next I will show you the model simulation of this case. And to examine the structure of the wave, I will show you the vertical cross-sections along those two blue lines. Here is the vertical motion from the different stage of this case. If you still remember the satellite pictures, it corresponds quite well with the real case, and it's growing and developing over the mountain and to the downstream of the mountain. And here is the mature stage, and after the cold front passed by, the wave decayed. This is potential temperature and the relative humidity. The white dashed line shows the relative humidity greater than 90%. Here is the mature stage. The oscillation is quite obvious over the mountaintop and to the lee side. And the maximum oscillation is at the inversion layer, which is around 1.5 to 2.5 kilometers. And the moisture is confined to the low level. And this is a decaying stage with no obvious oscillation. And if we check the wind conditions for this case, here is a time series, and this is before and the mature stage. The wind direction changed from southerly to southwesterly, and the shading shows the wind speed is getting stronger. And this is the U over N is also if you still remember the full number, the U over NH is the full number. So if the U over N is greater than H, which means the full number greater than 1. And for those developing and mature stage, there is a greater U over N along the time series. And the wave also elongated with stronger wind, and the maximum wind wavelength is at the inversion base, as you can see by the red shading, which means the wavelength is greater than 6 kilometers. And we also calculated the squirrel parameter during the developing and mature stage. You can see the L square, it has a maximum level at the inversion base. And below, and it decreases above and also below, which means the vertical propagation is trapped at the inversion layer. And here is the difference between the L square before the between the upper low level and upper level, and it's 0.69. It's over the threshold for the condition of Oahu for the trapped Lee waves to occur. So in a summary, the factors essential for the trapped Lee waves to develop is the strong low-level winds with full number over 1 impinging above the ridge top. And the wind shear should have increasing wind speed with respect to height through the stable layer, and there should be no critical level. And the third is the existence of a stable layer. The inversion can decide the distribution of the moisture, such as the level of clouds and the maximum amplitude. And the squirrel parameter is maximum above the ridge top and within the stable layer. The high-resolution model with the terrain in conjunction with the satellite picture are useful tools for the trapped Lee waves to predict and analysis. For the forecast implementation, during the winter time, if the atmosphere is stable and there is a prefrontal, there is cold front approach, the prefrontal southwesterly wind with increasing wind speed can create a potential environment for the trapped Lee waves to occur. And you can check the inversion layer, whether there is a layer and is it lifted above the mountaintop, whether the wind shear is getting, the wind speed at low level is getting stronger so that the full number is over the 1 and the airflow can go over the mountain, and whether the wind direction is shifted to perpendicular to the mountain, and also check the vertical wind profile if there is an increasing wind shear through the inversion level. And also the numerical simulation is a good tool to help you decide whether there will be trapped Lee waves. That's all my presentation for today. Thanks.
All right, thank you, Liye. Okay, so now we have a few minutes for questions. I'm a little new to this side of Zoom, so I'm not sure exactly where the comments went. But if anybody would like to pose a question. If not, I can make a few comments. Okay, all right then. I guess I wanted to just follow up real briefly then with past Pacific Desk students. Let me share my screen here. Okay, so in doing my homework before this webinar, I identified in all the talks, even though they're quite different, there are some similar themes that you'll find often in mesoscale meteorology. So the first of those is that the currents of the mesoscale phenomena are usually controlled by some sort of specific synoptic environment. So of course with Alison's, it's a hurricane. And then in Feng's, it's having trough nearby and having light winds over the island, that's a typical feature. And then with Liye, it's having, you have to have relatively strong flow going over the mountains, but you also need to have an inversion. You need some sort of stable layer aloft for those mountain waves to occur. And then of course you also need moisture in order to see them. And that brings us to the second point, and that's that the vertical motions involved with these mesoscale phenomena are they're difficult to measure and expensive to measure if you were to do observations. So the best way to research these things is with the mesoscale models. So if you're wondering why do they keep referring to these models, it's because that's the best way of looking at these types of features. And then lastly, again with the mesoscale models, so there's two main purposes to them. One is to improve the understanding of the phenomena, but then the other one is to improve forecasting. So these features often occur in timescales that are like over an hour or less than 6 hours. And so your typical global scale models are not going to help you very much with those kinds of features, spatially or in time. But the hourly output from, say, the WRF model can help you predict those, which is one of the things that Feng pointed out. Okay, so that's all, unless I'm not sure how to identify if I have questions.
There's been a lot of chat back and forth in the chat box, but I didn't see any questions. People introduced themselves and then said thank you. But...
Oh wait, Jennifer has a question for Liye. What is the resolution of the numerical weather models that are detecting mountain waves over Hawaii?
My simulation,
Okay.
The output is at 1 kilometer per hour.
Okay, and then also how reliable have you found these forecasts to be, and how far in time can you predict?
In my research is I'm doing the hindcast. So I'm using the CFSR to do the hindcast, but the simulation result is quite well. So yeah, so I guess for the forecast, if you have the 6 hour 6 hour prediction, you can get the more detailed 1 hour and at 1 kilometer simulation to see the wave.
Okay. Okay, and that's another good message for our students. You know, these mesoscale models, they can only be as correct as the initial conditions from the large scale model are to determine them. So like Liye is saying, you know, the hindcast is corrected, or it's determined to be correct. And so then, but if you're just doing a typical forecast with those models for a day and they're off, then they're not gonna push the mesoscale model in the right direction. Okay, so with that, then thank you everybody. Thank you especially to my panelists. You guys did great, and I hope I see everybody back for the next webinar in a couple of weeks. All right, thank you.
Thank you.
Thank you.
Thank you. Bye-bye.
Thank you.
Hi, James. Good to see you.